A recent breakthrough from the University of Toronto adds another fascinating layer to quantum physics: the observation of negative time. This is not just a thought experiment or theoretical construct. It is a phenomenon observed in a controlled quantum setting. In this video, we'll break down this extraordinary discovery, exploring its science, implications, and why it is so important for our understanding of the universe. We'll also delve into its broader context, comparing it with similar quantum phenomena, and discuss the lively scientific debate surrounding it. The experiment conducted by Daniela Angulo and Ephraim Steinberg's team aimed to measure how photons interact with matter, particularly how long atoms stay in an excited state after absorbing light. Using lasers and an apparatus carefully calibrated over 2 years, the team passed photons through a cloud of atoms. This interaction caused some photons to be absorbed, temporarily exciting the atoms before they returned to their normal state and re-emitted photons. The team measured how long the atoms remained in this excited state and found something completely unexpected: negative time. Let's use an analogy to grasp this. Imagine cars entering a tunnel at noon, but the first cars emerge at 11:59 a.m. This may seem impossible in our everyday understanding of time, but it accurately represents what the researchers observed with photons. The photons appeared to exit the interaction before they entered, revealing a temporal behavior that challenges classical physics. At first glance, this concept might seem absurd, even contradictory. However, in quantum systems, particles like photons don't follow the strict cause and effect rules we see in the macroscopic world. Instead, they behave probabilistically. Until they are measured, their actions exist within a range of possibilities that may defy conventional logic. The meticulous work involved precise measurements to rule out any experimental errors. Over 2 years, the researchers refined their methods to ensure the robustness of their findings. The novelty of this discovery lies in its experimental evidence. Although negative time has been theorized, this is the first time it has been observed and measured in a controlled environment. By showing that photons can spend negative durations in their interactions, this experiment opens the door to new ways of thinking about quantum mechanics, causality, and the flow of time itself. It's important to clarify that this discovery doesn't suggest time travel or contradict Einstein's theory of relativity. Instead, it shines a light on the peculiar behaviors of quantum particles, behaviors that often defy classical intuition. In the quantum world, particles like photons do not adhere to fixed trajectories. Instead, they exist in a realm of probabilities. The negative time observed in this experiment reflects this probabilistic nature, where events don't follow a straightforward timeline. Instead, they occur across a spectrum of possibilities, some of which manifest as negative durations. To understand its significance, we can place negative time within the broader context of quantum phenomena. The delayed choice quantum eraser experiment, for example, revealed that decisions made in the present can influence the past states of particles. Similarly, quantum tunneling demonstrates that particles can instantaneously pass through barriers, challenging our classical understanding of time and space. Another fascinating connection is the study of superluminal group velocities, where light waves appear to exit a medium before entering. While this doesn't violate causality, it reveals how wave functions and phase shifts can produce seemingly paradoxical results. Negative time fits within this framework, further illustrating the non-intuitive behavior of particles at the quantum level. The discovery also prompts us to reevaluate how we model interactions in quantum systems. By refining our understanding of these interactions, scientists can adjust existing theories and develop new ones to better explain the universe's fundamental workings. Negative time may even provide insights into unifying quantum mechanics with classical physics, an enduring challenge in the scientific community. On one hand, The discovery represents a bold new observation that challenges established norms. On the other hand, some critics argue that the term negative time might be misleading. German physicist Sabine Hossenfelder has been a prominent critic, suggesting that the observed phenomenon is better understood as a phase shift in photons rather than a reversal of time. According to her, calling it negative time risks over-sensationalizing what might be an artifact of measurement rather than a breakthrough in understanding time itself. However, Angulo and Steinberg defend their terminology. They argue that negative time accurately encapsulates the observed behavior and invites further exploration of its implications. While the phenomenon may not be intuitive, it highlights gaps in our understanding of how light interacts with matter, opening new pathways for research in quantum mechanics. Beyond theoretical implications, the discovery raises exciting possibilities for technological advancements. For instance, quantum computing is a transformative field that emerged from understanding how quantum particles behave in superposition and entanglement. Unlike classical computers, which process data in binary, zeros and ones, quantum computers use qubits that can exist in multiple states simultaneously. This capability exponentially increases processing power, allowing quantum computers to solve problems, like optimizing complex systems, breaking encryption, or modeling molecular interactions that are beyond the reach of classical computers. Similarly, atomic clocks, which rely on quantum transitions within atoms, have revolutionized timekeeping. By measuring the vibrations of atoms with extraordinary precision, atomic clocks enable technologies like GPS navigation, telecommunications, and even financial systems that depend on ultra-accurate time synchronization. Without quantum mechanics, these precise measurements would not be possible. Another area is quantum cryptography, which uses the principles of quantum mechanics to create unbreakable encryption methods. For example, quantum key distribution, QKD, ensures secure communication by leveraging the quantum property that any attempt to measure a quantum state disrupts it. This makes it impossible for hackers to intercept or eavesdrop without detection, laying the groundwork for the next generation of cybersecurity. While negative time itself may not immediately translate into a specific technology, its study could deepen our understanding of light-matter interactions and temporal mechanics, potentially leading to innovations in fields like photonics, communication systems, or even time-sensitive quantum measurements. As history has shown, seemingly abstract discoveries often catalyze practical advancements we can't yet envision, underscoring the importance of curiosity-driven research. Thank you for watching and joining us on this journey into the quantum realm.